All right, so this question says express or write the expression in terms of x and y only. So when we're done, there should be no sine, tangent, cotangent, secant, cosecant, cosine. There should be no trigonometric functions left over when we are done. Okay? Lots of things going on here. Okay? There's understanding of composite functions. Okay? It's a composite function. There's understanding of trigonometric inverses. Okay? Then there's going to be an understanding of trigonometric sum and difference formulas, specifically the cosine one. A lot of dynamics going on here, and if we can get some realized success with this, solving just one problem tells me you know a lot of stuff. You've learned a lot of stuff about trig. Okay? Also tells me you know some stuff about college algebra as well. All right, so what we want to look at here, this is cosine of this other garbage inside the argument for cosine. So it's a nested or a composite function. And with those, we always go inside out. Start with the inside, work our way out. So we're going to start with the expression that says sine inverse of x minus tangent inverse of y. And I'm going to highlight these, one green, one blue. Okay, so that we can, it's just easier to talk about them. Okay, the green one is sine inverse of x. What is that x? What is that for our sine inverse function? It's an input, but it's the input. What type of input is it? What does it represent? What is it? What? It's a ratio. A ratio of what? Because it's sine, it's a ratio of opposite over hypotenuse. So this input is a ratio. So when they write this, okay, they are really telling me an angle. Does that make sense? Because the output of that function is an angle. Okay? So they're implying some angle. And that angle is going to have an opposite side, that is x, and a hypotenuse, that is 1. Does that make sense? So let's draw a picture for that angle. Now it's a sine inverse, so it can only work in these two quadrants. That's all it's defined for. Okay, first and fourth. It's a positive x, and if x is the opposite side, and it's positive, we know that that's got to be in the first quadrant. The hypotenuse is 1. Okay? The angle that they're telling me is that angle right there. Okay? Now, I don't have a specific value for that angle right now, so I'm just going to name it alpha. Is that okay? All right. Now, we can either do this now or we can do it later, but we're going to need this distance right here. Okay? So the Pythagorean Theorem tells me that distance should be 1 minus x squared, all underneath the square root. And that's saying if I called that distance b, we could say b squared plus x squared equals 1 squared. Solve for b, and it gives you that. Is that okay with everybody? So that sine inverse of x, the input of the ratio of x over 1, is going to output alpha. Okay? Now let's deal with the blue one. Tangent inverse. Tangent inverse, again, is only defined for these two quadrants. Okay, between negative pi over 2 and positive pi over 2. And because tangent is opposite over adjacent, and this is y over 1, I know I should reside in the first quadrant because of the positive aspect of that y. Is that okay with everybody? Okay. If it was negative y, I would know I'd be in the fourth quadrant, and I would know that the y is negative and the 1 is positive. Pythagorean Theorem tells me that this distance here, 1 plus y squared, underneath the square root, right? That function produces an output that is an angle. It's that angle right there. I'm going to call it beta. So what this really turns into is cosine of alpha minus beta. Does that make sense? Okay. And now because we have the images here for our alpha and our beta, we can use our, in this case, it'd be the difference formula for cosine that says cosine of the first angle times cosine of the second angle. And then you use the opposite sign, so that's a minus, we're going to use a plus. And then sine of the first angle, sine of the second angle. Do you know cosine of alpha? You now know it's radical 1 minus x squared over 1, right? It's adjacent, or it's this adjacent side divided by the hypotenuse. That's why we ended up needing that value there, or that expression. Do you know cosine of beta? It's 1 over root 1 plus y squared, right? Do you know sine of alpha? Sine of alpha, x over 1. And you also know sine of beta to be y over root 1 plus y squared. Now, if we multiply this, so that's all the trig. Now it's just algebra, okay? So I'm going to multiply these together. It gives me root 1 minus x squared over root 1 plus y squared. This gives me xy over root 1 plus y squared. Do we have a common denominator there? Okay, so then we can rewrite this now as xy plus root 1 minus x squared over root 1 plus y squared. And what that does, so that right there is the exact same thing as that right there. It looks messier, but it has now removed all knowledge of trigonometry, right? Okay. So if I wanted to evaluate this thing, all I now need is x and y. I don't need to know what angle is attached to x and what angle is attached to y for specific values of x and y. Okay, which I wouldn't need to know if I was going to use that original expression they provided us with. Okay. Now, would you guys agree it's a pretty lengthy problem? Be nice to check, wouldn't it? Okay, so we can do this. We can graph this. Okay, now we have to. You can do it in Desmos. You do it in GeoGebra. Doesn't matter. I like doing it in GeoGebra because, like, I call this like f of x, and I call the other one g of x. If I'm going to do it in Desmos, it doesn't know function notation. So if I type in cosine of sine inverse of x minus tangent inverse of y, hit enter like that. If I type that in Des or in GeoGebra, it'll graph it. Okay, but here it doesn't graph it. It tells me try adding an equal sign. Okay, still doesn't know what to do. Okay, so what I need to do, I need to actually identify as y equals. Does that make sense? Okay, and it gives me that graph right there. Pretty odd looking graph, right? Okay, now we just found algebraically that it is xy plus the square root of 1 minus x squared all over the square root of 1 plus y squared. Okay, now again, doesn't know what to do because it needs it as an equation, so I'll say y equals, and does it produce the same curve then? Okay. Which now, obviously, if I were to say, another way of doing it, if you don't want to graph it, okay, now it doesn't know, and I don't know if I can define x to be, let's say x has got to be a ratio between -1 and +1. So I should say 0.5. And y has to be also a number. Now the inverse for the tangent, that means y can be anything. Okay? And that should be division there. I don't know why that. So let's say y is 2. Okay? I didn't think it would evaluate this because of x's and y's. So what I'd have to do is take every x and make it an a, just so I can get it to evaluate. I'll make that a. And I'll make every y b. This one needs squared. And there we see, as long as you see when I get outside, when a is outside of 1 and -1, it's undefined, right? So I'm going to make that go between -1 and 1, okay? I'll always be defined between those two, okay? And then it doesn't matter what b is, okay, because it's coming from the tangent inverse, and that input can be any number. So if I play those and then just randomly stop them, same result. That kind of makes sense on how we could check that? Okay. The next one I want to do is, it's actually, I think, a little bit simpler. Maybe I should have done this one first. This is using specific angles. Okay. So we got sine of cosine inverse of radical 2 over 2. Previously, the radical 2 over 2 was x. And then tangent inverse of radical 3, previously the radical 3 was y, right? So those are specific ratios, where in the last example we had all ratios, generic ratios. Does that make sense? Okay. So now it might be a little bit easier to evaluate this or to realize what we're really doing here. If I go cosine inverse of radical 2 over 2, so cosine inverse is only defined for those two quadrants. Which angle measurement has an x value? Because that's what this is. Ultimately, this is asking, what angle measurement has an x value of radical 2 over 2 in the first or second quadrant? 45. So this is really saying sine now of 45. Plus now this is saying, okay, which angle measurement in either the fourth or first quadrant has a sine divided by cosine that gives me radical 3. Say again. First quadrant, and 60 degrees. Okay? First quadrant, and it's 60 degrees. If I divide, so 60 degrees is 1/2 comma radical 3 over 2, right? Divide those, radical 3 over 2, and 1/2, you get radical 3. So 60 degrees. So this question is really asking, what is the sine of 45 plus 60? Or ultimately, what's the sine of 105, right? Which is something we don't know from the unit circle. So because I've got it now as a sum, I can rewrite this as sine 45 cosine 60 plus cosine 45 sine of 60. So sine of 45 is radical 2 over 2. Cosine of 60 is 1/2. Cosine of 45 radical 2 over 2. Sine of 60 radical 3 over 2. That gives me radical 2 over 4. That gives me radical 6 over 4. So because they're both over 4, there's my final result. That's the sine of 105, which is identical then to that thing right there. That make sense? So we could check that, and I'll just, while you're writing that down, I'll come to the side and type it in Desmos. So you can see here, if we type in the original expression that we started with, sine of cosine inverse of radical 2 over 2 plus tangent inverse of radical 3 gives me that number right there. If I type in radical 2 plus radical 6 over 4, gives me the same number, right? Okay. And the nice thing about this is that it removes all trig functions, and we're left with just a numerical value. Okay. Is that okay? I think those are especially example 7, okay, and example 4 that we did yesterday. I think those are some of, if not the most difficult types of questions that we will see, I think, in the whole course. Okay. Now, some of you might say, well, some of the equations that we see later on will be more difficult. Maybe some of the identity work that we've done is more difficult. But I think there's so much going on here, and there's somewhat of a level of abstraction, I think, that occurs when I see, especially this one here, when I see sine inverse of x, to know that that is giving me this angle alpha and ultimately this picture that's attached to it. Okay, I think that confuses people. What I would like to do is introduce these to you. Okay. And I know I'm not just going to give them to you like this and say memorize them. I'm going to show you where they come from. It's a very easy connection from what we already know. Okay, so these are called our double angle formulas, and if we were to say that there's a proof for these formulas, it probably wouldn't be called a proof because they are an extension of our sum and difference formulas. So most likely these things would be considered like corollaries, or sometimes they call them lemmas, which is just something that is easily shown or demonstrated or proven using kind of like a parent theorem or parent property. Does that make sense? Okay. So let's just start with this concept that we talked about in the last 2 days. We said that if we have, let's just start with the sine. If I had sine of alpha plus beta, that's a sum of two angles. Okay, so we rewrite that as sine of alpha cosine beta plus then cosine alpha sine of beta, right? When it's the sine function, it goes sine, cosine, sine, S-I-G-N, cosine, sine. Okay, alternates back and forth. Today, what we're going to be interested in is asking, well, what does sine of maybe 2 alpha or 2 beta look like? Okay, so here's my question. That's multiplication, right? Can you rewrite multiplication as addition? You can rewrite this as sine of alpha plus alpha, right? Okay, so if I did that, the only thing that would change in this row up here would be that beta is now being rewritten as alpha, right? So then doesn't that get rewritten as alpha and that get rewritten as alpha? And what we would be left with is sine of alpha, cosine of alpha, plus cosine of alpha, sine of alpha. Good. So what are we seeing about those two things? They're the same. So you got 2 of them, right? So 2 sine alphas, cosine alphas, which gets me back to this double angle. It says sine of 2 alpha is the same thing as 2 sine alpha cosine alpha. That's our double angle formula for sine. Okay? And my hope is that we realize that that came from something we already knew, right? We already knew the sum formula for sine. Okay? But what that does is basically says, okay, let's just arbitrarily say I didn't know the sine of 60. So I didn't know the sine of 60. Let's draw a unit circle here real quick. Let's say I'm looking for the ordered pair for 60 degrees. And we don't know it. But we do know the ordered pair for cosine, or sorry, for sine and cosine of 30 degrees, right? We know that information. Can I say that the sine, let's say the sine of 60 degrees, can that be rewritten as the sine of 2 times 30 degrees? Where that 30 now is your alpha. Does that make sense to everybody? So now I can rewrite this as 2 sine of alpha, which would be 30, cosine of alpha to be 30. So you're able to eventually, we're going to run through this evaluation here in a moment, and we're going to be able to find that y value on the unit circle by knowing everything about this other smaller angle. What's the sine of 30? 1/2. What's the cosine of 30? What happens to that 1/2 and that 2? You're left with a radical 3/2, right? So we're saying that the sine of 60 degrees is radical 3/2. Is that something that we knew or have alternate pathways defined? So that confirms that this formula does indeed work. That relationship is true. Okay? So that's the sine double angle formula. Let's do this one. Let's go cosine of 2. Let me use my alphas sometimes look like 2s, so let's use 2 beta. Doesn't matter what variable you want to use x. Doesn't matter. Is that the same thing as cosine of beta plus beta? Using the same approach as before, right? Cosine of a sum of 2 angles is written this way. Cosine beta, cosine of first angle beta, cosine of the second angle beta, and then whatever that sine is, we do the opposite over here. And then we go sine of the first angle beta, sine of the second angle beta. Okay? Previously, if we go back up to the last section, this was S and T. This would have gone S, T, S, T. But now they're both the same. What does this turn into? Cosine squared beta minus sine squared beta. Okay? So the cosine of 2 beta is equal to that. Which now let's go ahead and use what we know about 30 degrees. I go cosine of 2 times 30. Okay, so I'm interested in cosine of 60 degrees. I can find that by knowing the cosine of 30. So this would be my beta now. What's the cosine of 30? Radical 3/2. We'll square that, right? What's the sine of 30? 1/2. We'll square that. What's radical 3/2 squared? 3/4. What's 1/2 squared? 1/4. What's 3/4 minus 1/4? So we go back up to my unit circle. Is the cosine of 60 supposed to be 1/2, like that formula says it is? Okay. Now, and this one's unique, but there's alternative formulas for the cosine double angle. If I write, so cosine of 2 beta was equal to cosine squared beta minus sine squared beta. Okay? And in order to evaluate cosine of 2 beta, using that formula, I need to know something about, I need to know the cosine and the sine of 30 degrees when we were doing that, right? We should be able to make that a little bit simpler, be able to still be done, but not needing to know both coordinates of 30. Because of this. Don't we know that sine squared x plus cosine squared x equals 1? So can't I replace that right there with 1 minus sine squared beta minus then sine squared beta? And what's that going to turn into? Is that 1 minus 2 sine squared betas? So now we can write that. So now here's the question. You could say, well, now I can figure out what the cosine of 60 is if I only know what the sine of 30 was. You know sine of 30 to be what? 1/2. What's 1 minus 2 times essentially 1/4? So if I, let's just do, if I want cosine of 60, that's equal to cosine of 2 times 30. So we go 1 minus 2 sine squared of, now beta would be 30, right? Okay. So I go 1 minus, what is the sine of 30? 1/2. So if I square that, I get 1/4, right? What's 1 minus 2/4? 1/2. Is the cosine of 60 1/2? And all I needed was the sine of 30 to generate that. Okay? Let's say I didn't know the sine of 30, but I knew the cosine of 30. Let's do this. Let's go. It's the same relationship right here. Okay? We replace cosine with 1 minus sine squared, right? Can I replace sine squared instead? Okay, so give myself a little bit more room here. If we go cosine of 2 beta is equal to cosine squared beta, but now minus sine squared. I'm going to rewrite sine squared using this thing. We'll say sine squared is 1 minus cosine squared. And it's a quantity, so I got to put in parentheses like that. And now I got cosine of 2 beta equals cosine squared beta minus 1 plus cosine squared beta. So that's 2 cosine squared beta minus 1, right? That's another formula for cosine of 2 beta. Well, let's think if I wanted a cosine of 60, that's the same as cosine of 2 times 30. So now that would be the same as 2 cosine squared of 30 minus 1. So that's 2. What's the cosine of 30? Radical 3 over 2. If I square that minus 1, then what's radical 3 squared? Okay, 3, and that's going to be 4. So I got that minus that. So now I get 6/4 minus 4/4. Still 2/4 or 1/2. So we just found the cosine of 60 by only knowing what the cosine of 30 was. Does that make sense? Okay. So those are the 3 formulas that we're allowed to use, we have at our disposal for cosine of a double angle. You can use any one that you want. But if I start giving you problems that maybe I start you off with, hey, find cosine of 2x. But then I tell you, knowing that the cosine of 1x is like 2/3. If you were going to do that because I gave you the cosine of x to be 2/3, you probably want to use that third double angle formula for cosine because it only uses the cosine of 1x, right? Okay. I can substitute that 2/3 in there right away, evaluate, and now I've got the cosine double angle. Okay. If I gave you a problem that said, find the cosine of 2x knowing that the sine of x is 2/3, then you'd use that middle one because I'm giving you sine, right? If you want to use that top one, which is applicable sometimes, you would have to, if I gave you the cosine, let's say, find a double angle for cosine, if the cosine of 1x is 2/3, you'd have to draw a picture. Cosine of x is 2/3. Find what the sine then would look like, use Pythagorean Theorem, and then you can use that top one, okay? But these are applicable depending on what you were provided in the original problem. Okay. I'm going to give you one more question, one more example that we have to decide, okay, which one of those three is applicable to this problem. Okay. It says rewrite cosine of 3x in terms of cosine x. So what we're going to try to do here, and we're trying to build right now, what these formulas are going to do, or what they help us do, is build a toolbox to get equations in a format that we can solve later on. So give you a kind of a sneak peek of what's going to happen in a couple days, probably by the end of the week. Hopefully we're doing this. I'm going to give you the question: solve the equation that for cosine 3x equals cosine of x. And I want to solve it analytically. I don't want to use a calculator. Okay? This is a difficult problem because those two things are different. Okay? When we solve trigonometric equations, we like the arguments to be identical. Okay? It just makes things so much easier. Okay? So what we are going to do here is try to get them to be identical. And the best approach to do that is to depreciate this, to make the 3x go down to 1x. Okay? So this is the first step to this. So if this was the overall question, the first thing you would do would be that right there. Okay? So we're going to try that. We're going to start with cosine of 3x. And we're going to try to dwindle it. Okay? So this can be done no matter what that 3x is. If that 3x is 4x, if it's 5x, 6x, 7x, it does not matter. Okay? When we get beyond 3x, it gets very tedious. Okay? But the procedure is the same way, the same structure. You know that 3x is the combination or the sum of two smaller things, right? Can you do that? Is that still cosine of 3x? Okay. So every single time that I give you an argument that is not 1x, but it's 2x or 3x or 4x or 5x, you can always break it down into a sum. Okay? I like to break it down just because of in the way my mind works. I always like to break it down to an even value and a singular odd value. Okay, so like if this was 5x, I'd break this down to 4x plus 1x. Does that make sense? Okay. But once we know what cosine of 3x, maybe once we have cosine of 5x, it might be better to break it down to cosine of 3x plus 2x. We'll just depends on what we have at our disposal at that moment. That will make a logical sum here. But now that I have that, can we go off of what we learned in section 7.2 and say that cosine 2x plus x looks like this? Cosine of the first angle times cosine of the second angle, right? Then the opposite sine, sine of the first angle, sine of the second angle, right? Okay. Now, think about this as we move on. We want only cosine left over. So when I go back up here, because I got a double angle now for cosine, right? When I go back up here and look at my properties, my formulas, I don't probably want to use that one. It's not wrong to use that one. It's not wrong to use that one. We could put those in, but it's going to create one more substitution that's unnecessary. Does this one incorporate only cosine? So we're going to replace cosine 2x with 2 cosine squared x minus 1. And that will still be multiplied then by this cosine x. Okay. Now, that there is a double angle as well. So we're targeting all of these double angles and trying to simplify them. Well, that goes down to 2 sine x cosine x. But then we still got that times sine x there, right? Would you guys agree I can distribute that cosine right there? So it gives me 2 cosine cubed x minus cosine x. When I multiply these together, it's going to give me minus 2 sine squared x cosine x. Now think about what our overall problem was. Get it down so it's just cosine of 1x. Can we now do that because of this sine squared x? What is sine squared x the same thing as? One minus cosine squared x. That's the Pythagorean identity, right? So now when I take this negative, so what, and I don't want to rewrite this, but that right there is the amount that needs to be distributed to this parenthesis, right? So I'm going to have negative 2 cosine x times 1, so it'd be negative 2 cosine x. And then negative 2 cosine x times negative cosine x, so it becomes positive 2 cosine cubed x, right? In this, I don't know why I changed that from a 3 to a 2. That should be a 3. 3. There's 3 right there, so I don't know why I didn't change that. So now you have 2 cosine cubes there, 2 cosine cubes there. You have 4 cosine cubed x's, right? You have then minus 3 cosine x's. Okay. So now cosine of 3x is equal to that thing there. Is that okay with everybody? We can prove that graphically. You know, just type in cosine of 3x. I get that. Type in 4 cosine of x cubed minus, was it 3 cosine x? Do the graphs end up being the same? Okay. So remember what our goal was. Our goal initially was to be able to maybe solve this. And we'll get to this question later on down the road. Okay? But if I want to solve that, then the question is, where does essentially cosine of 3x, so geometrically, it'd be where does the black and red curves cross, right? Okay? What we would really be doing, or what we would want to do to end up solving this equation here, is to rewrite this like that. Is that okay with everybody? So now the equation would look like this, equals cosine x. So those two equations are identical now, okay? Which allows me to now say, I'm going to rewrite this way, 4 cosine of x cubed minus 3 cosine x minus cosine x equals 0. That's what I would write. Does that make sense? That is saying the exact same thing that this says. Then what I would do is say, I don't like all those cosines in there. I'm going to go to the side, I'm going to say, let u equal cosine. And we have that then, right? Can I then rewrite that as u, and then 4u squared minus 3 minus 1 equals 0? And so that'd be 4u squared minus 4, right? Can we factor that? Can you factor that using polynomial techniques? Does that make sense? So I would get u equals 0. That would be 1, right? Okay. And then there in the middle, I would get, so I'd add 4 to both sides, so I get u to be plus or minus 1. Does that make sense? Okay. So what would happen there would be u equals 0, u equals negative 1, or u equals 1. Well, then u was what? It was cosine of x, wasn't it? Where does cosine of x equal 0? At what angle measurements? Careful, when is cosine 0? Isn't that pi over 2 and 3 pi over 2? And then when is cosine negative 1? That's the 180 one, right? That's the pi. And when is it positive 1? 0 or 2 pi. And those, if we were to look at the graphs of the two parts that we start with, cosine 3x and cosine x, that's where they're going to cross. So that's why we'd want to be able to use these formulas. Okay? That's where we're headed towards the end of the week. Have a good one.